seating in a fancy dining car.
Okay, well, those are some interesting videos about reaction, but now we're going to get to the chemistry of it involved, and that's reaction rates, okay? So we're going to talk about reaction rates. So here we go. Alright, when we talk about reaction rates, we need to talk about what that means, alright? And then a chemical reaction occurs at a certain rate. Now, you just can't throw some chemicals somewhere and time it and then throw some more chemicals in and time it, because that's not what it's all involved. It's not just about the time that it takes for a reaction to occur, okay? So, what also is going to be involved is the change in concentration over that time. So, reaction rate. Alright? And so, when looking at this, we'll look at something like reaction between baking soda and vinegar. Now, put those together, that reaction rate in a classroom setting would be pretty quick. Alright? Happens pretty fast. But if you look at like reaction rates of like fossil fuels, it takes a long, long time for fossils to break down and eventually make our crude oil that we like to take out of the ground. So what is the reaction rate? Reaction rate is the change in concentration of a reactant or a product per unit time, expressed as this right here, molarity per second. Okay? So molarity per second. So you can think of this similar as like miles per hour. Okay? The rate at which you are going down the street in your awesome car. Right? So, molarity per second, the change in the concentration divided by the time. With all that being said, here's our lovely calculation. We're just going to do average reaction rates for this class. So the average reaction rate is, there's that symbol again, delta. Delta quantity, that means the change in quantity, change in how much concentration you have, divided by delta time, which means the change in time. Delta quantity, the final concentration, alright, it says amount there, that's meaning concentration, minus the initial concentration. Delta time, the final time minus the initial time, alright? So right here is how we're going to calculate your lovely reaction rate. With that said, we might as well look at a sample problem. In a reaction between butyl chloride and water, the initial concentration of butyl chloride was 0.220 molar at time 0. Right? And the concentration at time 4 seconds. So 4 seconds later, the concentration is now 0.100 molar. Calculate the average reaction rate over this time period. Right? So when you're doing these, once again, alright, it's going to be the change in concentration over the change in time. Let's write down what we know. It's already done for us here. We know that the time starts at 0 seconds and ends at 4 seconds. Alright? We know butyl chloride, that's this formula here, it starts at a 0.220 molar solution and ends at 0.100 molar. Okay? So it goes from 0.220 to 0.100. Right? This is just an easy plug and chug equation here. So, what do we want to find out? We want to find out the reaction rate, molarity per second. What we got to do, simply plug this in. Here's our equation here. Average reaction rate equals delta quantity over delta time. We scroll some down here. Our delta quantity, we have the final, right? The final concentration minus the initial concentration divided by the final time minus initial. Alright, since this is a rate, this is decreasing. For purposes of this class, you can just do the absolute value of this, so keep them all positive numbers. If you did a negative, what that would mean is you would know you were losing, alright, this concentration of whatever you're calculating. If it was a positive number, then that concentration would be increasing. Alright, so if I subtracted these two, 0.1 minus 0.22, you'd get 0.120 molar. So there's the change in concentration. 4 seconds minus 0 seconds is 4. Plug this into our handy calculators, and we get 0.0300 molarity per second. And that's the calculation of reaction rate. Okay? So the calculations in this part of the chapter, very, very simple, very, very straightforward. Alright? Once again, reaction rate that we'll calculate is the average reaction rate, which is the change in quantity. So how much the concentration changes divided by the change in time.
You can see right there, Matt Kenseth just gets into that left front of Jeff Gordon, and Gordon goes up and gets in the side of the 71. Gilliland, nowhere for Kurt Busch to go. Brian Vickers, and they just stack up from there.
Look, that's a six-pack into the wall, just all in one move.
And this is the way the big one works at Talladega. I saw cars running in the top.
Moving right along. All right, we're going to talk about how reactions occur and how we can speed them up and slow them down. Collision theory. All right, for this little segment, I'm going to use a marker to explain these. Okay, use a marker to explain these, and hopefully it'll work. So what is collision theory? Well, first of all, this is what collision theory says. It says particles must collide in order to react. That makes sense. If I take a box of baking soda and a container of vinegar and place them on top of each other, they're not going to react. All right? The vinegar and baking soda might have to be poured into each other, then they'll react. So what it's saying is, for particles to collide, to react, they first must collide. All right? If I have this lovely marker here and this lovely marker cap here, right? For them to, we'll say these are reactants. For our product, we need a complete marker with cap. So they must actually collide in order to react. They don't hit each other, they're not going to react. Makes sense. Alright, so for any reaction to occur, particles must come in contact with each other, and only a small amount of these actual collisions actually make your product. A lot of things will collide and not make the product, and we'll talk about why in just a second. Alright, orientation. Particles must collide with correct orientation in order for this reaction to take place. Once again, I'll have my marker cap and my marker. Alright, let's see. We said they must collide, but if I put the marker together, well, they're colliding, but I'm not making my complete marker. Well, how does it need to collide? Well, the cap and the marker need to collide just right, the correct orientation. So, particles collide must have the correct orientation in order to react. Right? Now, when this correct orientation occurs, there's this intermediate thing that's made, and that's called the activated complex. You still might not have a product formed, okay? So it forms this thing called the activated complex. What is the activated complex here? Well, alright, the activated complex is a temporary, unstable arrangement of atoms. It may make the products, or it actually can break back apart and reform the reactants. So, activated complex is like here. It might go forward and stay a product, stays a marker, or it could all break apart and form your reactants back. So that is what an activated complex is. Alright, so we know for a reaction to happen, you must have a collision, you must have correct orientation, and then one more thing, you must have this thing called activation energy. Alright? This is the minimum amount of energy required for a reaction to occur. Alright? An activated complex will not form unless this energy is there. Okay, so activation energy, once again, the minimum amount of energy that leads to a reaction. Now, every single reaction that occurs has energy that has to go into it for a reaction to happen. Yes, I know we've talked about reactions that are exothermic and endothermic. Endothermic energy goes in, exothermic energy goes out. What this means is the overall reaction is either exothermic or endothermic. Every reaction that occurs has energy goes in and energy that goes out. Right? What we term an exothermic and endothermic reaction to be is if overall, endothermic means more energy goes in than goes out, and exothermic means more energy goes out than comes in. Alright, what we're going to do is we're going to look at two graphs here for an exothermic and endothermic reaction. Alright, so we're going to look at two graphs here for exothermic and endothermic. Move these up a little bit so you can see them. All right, on the left side here, in case you can't read this, I'm gonna separate these two with a lovely line. Maybe I shouldn't do it in black, since everything else is written in black. Give me a second. We'll do it in blue. All right. This reaction right here is an endothermic reaction. So we got nitrogen plus oxygen gas give me nitrogen monoxide. All right, on the y-axis here, right, on the y-axis here, we have the potential energy. On the x-axis, we just have like time going on. So we've got energy being added. Now, from here to here, we have how much energy is in the original reactants. Okay? So this is how much energy is in the reactants. All right, this E sub A, if you can't see it here, write it larger. It says E sub A. This is the activation energy. How much energy it takes for this reaction to form an activated complex. So what has occurred is nitrogen and oxygen have collided with correct orientation and has enough activation energy. So you need this much energy to go into this reaction. Activated complex is formed. It has one of two options. It can either go back, reforming the reactants, or it can make our product. This is how much energy goes in. All right, when I look at this, I told you every single reaction has energy that comes in, and this is the energy that goes out. Okay, so this area right here is how much energy goes out of the reaction. If I compare how much energy went in to how much energy went out, all right, I can see a lot more goes into this reaction than comes out. So, if a graph looks like this, we call it endothermic. All right, this is an endothermic reaction. More energy comes in than goes out. All right, if I go to the other side here, we'll see this is how much energy we're starting with, how much energy is present inside the hydrogen and oxygens. So for this reaction, I got two hydrogens. A hydrogen gas plus oxygen gas gives us water. We've done this one before. So this is how much energy we already have. All right, right here, this right here is your activation energy. All right, so right there's your activation energy. Here's how much energy must go in. And then, from here way down to here, this is how much energy goes out of the reaction. So, energy in, right? Energy out. For this one, you have a little bit that goes in and a whole bunch that goes out. So, we call this an exothermic reaction. Right? So, this graph shows us endothermic reaction and the energy that goes in and out. This is the exothermic reaction graph. You can see they're very similar, but they're opposite.